Kenichiro Hashimoto from the University of Tokyo. Okay, first of all, I'd like to thank the organizers for giving me a good opportunity to talk about our recent activities at this very nice workshop. Okay, so today I'd like to talk about randomness effect on the charge glass formation in theta type BEDT-TTF compounds. Okay, so before starting my talk, I would like to thank my collaborators, especially the member of Sasaki Group in Tohoku University. And also I would like to thank Jens Mueller and Michael Lang, and the member in the Frankfurt University, because I spent 1 month, 2 years ago. Yeah, and yeah, we had a very nice, good collaboration of noise and thermal expansion measurement in this theta type compound. Okay, so this is the outline of today's my talk. First, I will give a brief introduction of the charge glass formation phenomena and charge liquid crystal glass state in theta BEDT compounds. And then I will show the result of the comparison of charge crystal and charge glass states in 3 different theta type compounds. And then I will talk about the charge crystallization process proved by a thermodynamic quantity, and also randomness effect on charge crystallization and vitrification. And then I will summarize. I will summarize my talk. Okay, so let me start my talk. So usually when liquid is slowly cool down, then actually crystallization occurs at the melting point. However, in glass forming liquid, when crystallization is avoided by rapid cooling, sometimes a glassy state can be realized. And this can be understood by the entropy versus temperature diagram. And it is believed that this supercooled liquid state with large viscosity can enter this glassy state at a glass transition temperature. And actually, the physics of glassy materials is still hot topics in solid state physics. And so in many special issues treating glassy materials, you can have many opportunities to see the importance of the glassy materials. And actually, there are several key concepts to the understanding of glassy materials. And for example, it is well known that in glass forming liquids approaching the liquid glass transition temperature, its viscosity increases and slow dynamics, and the dynamics start to slow down. And so it's believed that this is related to dynamical heterogeneity. And in many glassy materials, slow heterogeneous dynamics has been observed in both space and time. And these phenomena can be understood in terms of the energy landscape, as shown here, where a number of local minima corresponding to the metastable states, as well as crystal states coexist. And in this situation, when the liquid is cooled fast enough, then system can be trapped within the metastable state, and the system transformed into a glassy state. So this is the notion of the energy landscape for glass formation. And very interestingly, in strongly correlated electron systems, a wide variety of glass formation phenomena has been observed in various degrees of freedom of electrons, such as spin glasses, orbital glasses, and superconducting vortex glasses. However, the fundamental understanding of the glass formation mechanism is still an open question. Okay, so in this presentation, I will focus on the glass formation phenomena of the charge degrees of freedom of electrons. And actually, in the strong equality electron system, there are two representative insulating states driven by strong electron collision. One is the Mott insulating state in a half-field band system. The other is a charge-ordered insulating state in a quarter-field Hall band system. And the geometrical frustration effect on these two insulating states are very hot topics in condition matter physics. But yeah, today I'd like to talk about geometrical frustration effect on the charge degrees of freedom of electrons on frustrated triangular lattice, in which a charge graph state can be realized due to the strong geometrical frustration of the triangular lattice. Okay, so so our target material are the theta-type BEDT-TTF compounds, which have a layered structure consisting of conducting BEDT-TTF layers and insulating anion layers. And the charge transfer between these two layers lead to a quarter field Hall band system with a two-dimensional triangular lattice. And for example, this theta rubidium zinc compounds shows a charge order transition due to the strong intercyclic interaction B at about 200 Kelvin. And at this charge order transition, the system transformed from charge liquid to charge crystal states. But very interestingly, so this charge crystallization can be avoided by rapid cooling faster than critical cooling rates. And then the system enters a glassy state where the charge carriers are randomly distributed. And it is well known that the charge ordering temperature and the critical cooling rate for the charge gas formation can be controlled by the anisotropy of the triangular lattice, B1 versus B2. Yeah, and it is well known that the geometrical frustration between this B1, B2 plays an important role for the glass formation, charge glass formation in this system. Okay, so in this presentation, I will focus on the this theta thallium zinc or thallium quartz compound, which has the most anisotropic triangular lattice. Okay, so in the theta thallium zinc or thallium cobalt, there are two different crystal forms with orthorhombic and monoclinic symmetries. And this orthorhombic one shows a horizontal charge order at 240 Kelvin, like this. And because the anisotropy of the triangular lattice is large, so you need a very rapid cooling rate to make charge class states. In sharp contrast, the monoclinic thallium zinc compounds shows a diagonal charge ordering at 170 Kelvin here. And although the anisotropy of the triangular lattice of this material is more anisotropic than that of the orthorhombic one. However, so you actually you can see the large difference. You have a very yeah, that's the resistivity is very sensitive to the cooling rate dependence. And so actually you can make a charge graph states by rapid cooling higher than the 50 Kelvin per minute. Okay. So as I already discussed, the this orthorhombic system can be understood by the anisotropy of the triangular lattice B2 versus B2 over B1, but the tendency of the monoclinic one that does not follow this trend, which suggests that different charge glass formation mechanism between these two systems, orthorhombic one and monoclinic one. So we decided to investigate the physical properties of these two systems. Okay, so first I will show the comparison of charge crystal and charge glass state in three different type compounds. Okay, so here are the temperature dependence of the three different materials. So, orthorhombic cesium zinc and rubidium zinc, and for the monoclinic thallium zinc compound. So the theta or cesium zinc compounds with the most isotropic triangular lattice shows any long-range charge ordering down to very low temperature, and the system enters the charge graph state at low temperatures. In contrast, theta rubidium zinc and theta thallium zinc show a long-range charge ordering at 200 Kelvin and 106 Kelvin. And this charge ordering can be avoided by rapid cooling. Okay, so you can make a charge crystal and charge graph state by changing the cooling rates for these two compounds. And here are the RNS plot of the resistivity data for these three materials. And so very clear RNS behavior can be seen for the charge graphs and the charge crystal states for all the sample, or all the materials. And the RNS gap of the this cesium zinc compounds shows a very small value, which is consistent with the fact that the system is very close to the phase boundary. And regarding this theta or rubidium zinc, so there are large difference in the optical gap, RNS gap between the charge crystal and charge graph states. However, if you look at the data of theta and thallium zinc compounds, so there is little difference in the RNS gap between the charge graph and charge crystal states. Okay, and such a difference can be seen in the optical conductivity spectra of these materials. Okay, so the optical conductivity spectra of theta or cesium zinc show very large low energy excitations, which is again consistent with the result that this material is located near the phase boundary. And so we measure the optical conductivity spectra in the charge crystal and the charge graph states. For okay, and as you can see, so there are a large difference between in the optical gap between the charge graph and charge crystal states. And actually, these observations are very consistent with the resistivity data. But yeah, if you look at the optical conductivity spectra of this monoclinic thallium zinc compound, actually there is a little difference between the optical conductivity data between charge crystal and charge graph states, but the optical gaps are very identical for these two states. This is also consistent with the resistivity data. Okay, so this is a comparison of the charge graphs, comparison of the optical conductivity spectra of the charge graph states for these three different materials. As you can see, so as the anisotropy of the triangular lattice increases, the spectral weight in the low energy region shifts to a higher energy region. So, and so actually, then so I want to discuss the mechanism of these different behavior in the optical conductivity spectra. Okay, so actually there are many theoretical calculations for the theta type BEDT-TTF compound, which have been done by extended Hubbard model like this. And here, so I will show the charge ordering pattern in the classical limit, where the transfer integral t is equal to 0. In this situation, when the this V1 equal V2, in the case of V1 equal V2, So the ground state includes various charge ordering pattern like this, and actually the ground states include vertical, horizontal, diagonal, and three sublattice charge ordered state. And this three sublattice state is very metallic. And I think the orthorhombic system can be categorized this region. And indeed, diffuse X-ray measurements have reported that there is some short-range threefold charge order in both theta or cesium zinc and rubidium zinc compound. And in contrast, actually, so when B1 is larger than B2, which is the case of theta M type system. So the ground state has many chain stripe charge orders along the B1 direction, which includes horizontal, diagonal, and disordered states along the B2 directions. And indeed, this in theta, this theta M times in compounds, diffuse lines corresponding to the superpositions of the insulating 2D whole stripe charge order has been observed. Okay, so from these experimental observations, we conclude that in the orthorhombic system, so the geometrical frustration of the equilateral triangular lattice lead to a charge graph state in which metallic threefold charge order occurs. In contrast, in the C-time compounds, so geometrical frustration of the isosceles triangular lattice lead to a charge graph states, where the charge graph state can be described by the superpositions of insulating twofold stripe charge order. And actually, so in the orthorhombic type system, so you have a metallic threefold charge order, then the low energy excitation becomes prominent. But in the monoclinic system, you have only insulating twofold stripe charge order, then optical gaps becomes very high, and the system becomes very insulated. I think this scenario can be naturally explained the difference of the optical conductivity and resistivity data observed in these two different systems. Okay, so next I will talk about the charge crystallization process probed by a thermodynamic quantity. So actually, in the present system, the amplitude of resistivity will reflect the charge crystallization progress, because in the charge superliquid or graph states, the resistivity becomes low, but in the charge crystal state, the resistivity becomes very high. So in this study, we in order to investigate the charge crystallization progress, we first we cool down the sample to low temperature, and then we heated the sample up to a certain temperature, and we kept that temperature during the charge crystallization progress while measuring the resistivity as a function of time, so like this. So we performed this experiment at various temperatures like this below the charge ordering temperature, and actually, so it can be clear seen that the amplitude of the resistivity, which reflects a degree of charge crystallization, first increases and then saturates at all the temperature we measure. And this crystallization time becomes slower with decreasing temperature, And then below 150 Kelvin, crystallization time becomes slower. Then the crystallization time draw this kind of dome shape. Okay, and from the resistivity, time-dependent resistivity data, we constructed a so-called time temperature transform TTT diagram like this. And the obtained TTT diagram is dome-shaped like this. And actually, this TTT diagram, actually very similar TTT diagram is also observed in rubidium zinc compound from a candle-sensitive group. And also very similar behavior can be seen in other glass charge glass forming liquids such as metallic graphies and even water. So we can say that the dome-shaped TTT diagram is very universal. Is universally observed in other in many glass forming liquids. Okay, so but in this study, in order to more qualitatively evaluate the charge crystallization process, we used the differential scanning calorimetry (DSC) technique, which is a very powerful probe to observe crystallization, melting, and glass transitions. In the DSC measurement, so you prepare a sample and a reference, and you see the temperature of them. If there is a transition, then so you should have a temperature difference between them. But in this technique, so the heat flow is supplied to compensate the temperature difference between them. Then so you can calculate the entropy change at the transition from the heat flow you supply by using this equation. Okay, so and actually in a classical glass material, so you can see glass transition, recrystallization, and melting related to the entropy change. Okay, so here is a result of the DSC measurement for theta rubidium zinc compound. So in this study, we cooled the sample down to a target temperature, and we kept the temperature of the sample during the crystallization, and then we cooled the sample down to a low temperature. And after that, we measure the DSC in the heating process. Okay, so this is a experimental result of the DSC measurement. So as you can see, so there are anomalies related to recrystallization and melting, but we couldn't observe any glass transition related glass transition. So yeah, so the entropy change at the glass transition may be very small to detect in the DSC measurements. So anyway, so we subtracted the baseline from the raw data, and we got this very nice results. And the crystallization, actually, the entropy change related to the crystallization can be calculated by subtracting area B from area A. So this, Then we obtain the entropy change related to the crystallization. And so here is a result of the DSC measurement. So these figures show the entropy change as a function of time measured at various temperatures. And so actually, these results show that the charge crystallization progress is crystallization progress obey obey to the this actually the charge crystallization progress can be given by this JMAK model by shown by this blue line. And I don't explain the details, but actually these results are very consistent with result of NMR performed by another sensory group. And from these time dependence of the entropy change at various temperatures, we constructed a TTT diagram for this Rubin-Zimmermann compound. And again, so we obtained a dome-shaped TTT diagram. And actually, this domed shape indicates that the crystallization progress is given by nucleation and the nucleus growth process. Okay, so then finally, I will talk about the randomness effect on charge crystallization and vitrification. So since organic materials are very clean, we expect that the charge glass formation is essentially essentially free from disorder. But actually, we recognize that there is a large sample dependence in the charge glass forming ability. So this is resistivity data of our Rubin-Zimmermann compound, which is provided by Yamamoto Group in Japan. And in our case, the critical cooling rate is about 30 Kelvin per minute. But in the previous results, it was 5 Kelvin per minute. So this difference may come from the different sample qualities. Then, so we decided to investigate how the randomness effects affect the charge glass forming ability by using molecular defect introduced by X-ray radiation. Okay, so it is well known that X-ray radiation is a powerful probe to introduce molecular defect in organic materials. And so this figure shows the X-ray radiation effect on the molecular vibration in a kappa type BEDT-TTF compound. And large suppressions has been observed in the CN bond in the anion layers compared to that of the BEDT-TTF compounds, BEDT-TTF molecule. So then, these results indicate that molecular defects are mainly introduced within the anion layers. Therefore, so X-ray radiation does not largely affect the physical properties of pi electrons, such as charge carriers. Okay, so this is the experimental setup for X-ray radiation, and we used tungsten tube to irradiate X-ray radiation, to irradiate X-ray to the samples. And we measure the resistivity, optical conductivity, and DS measurements for the X-ray irradiated sample. And for optical measurement, we use a sample. We change the irradiation time in the same sample by changing the lead plate as a function type, which work as a protection for X-rays. Okay. So this is a result of the optical reflectivity data for the X-ray irradiated sample. So as you can see, the so there is a very sharp peak around 2100 Kelvin, which is attributed to the CN bonding in the anion layers. And as you can see, the intensity of the CN peak decreases almost linearly as a function of irradiation time. But if you look at the entire spectra, which comes from the BEDT-TTF pi electron system of BEDT-TTF, so there is no difference with irradiation time. This indicates that molecular defects by X-rays are mainly introduced within the anion layers, not to the BEDT-TTF layers. Okay, then so we measure the DST. We perform the DST measurement for the X-ray radiated sample, and we found that this charge order and transition temperature is systematically suppressed by X-ray radiation like this. Yeah, and actually the charge order and transition temperature decreases almost linearly with the irradiation time like this. But the entropy change at the transition does not change with irradiation. So yeah, this indicates that there is no phase separation by X-ray radiation. Okay. Then, so we measure the resistivity. We measure the temperature dependence of the resistivity for each sample with different irradiation time. Okay, and so actually, as you can see, the critical cooling rate for the charge glass formation becomes slower with increasing X-ray radiation time, like this. And actually, for the Princeton sample, the critical cooling rate was 30 Kelvin per minute, but now it becomes 1 Kelvin for 100-hour irradiation. Okay, and so in order to qualitatively evaluate the charge crystallization progress for the X-ray irradiation, so we plot the amplitude of resistivity at 150 Kelvin within the critical cooling rate versus irradiation time diagram. And yeah, so this red color indicates the large resistivity regime corresponding to the charge crystal states. And this blue color corresponds to the charge graph states. And it can be clearly seen that the critical cooling rates plotted by white colors separate two states. Okay. And yeah, from these results, we can say that the charge crystal regime is significantly suppressed by randomness introduced by X-ray. Yeah, and so next I will show the result of the optical conductivity data. So we measured optical conductivity at each point in this figure. And for the Princeton sample, as already discussed, there is a large difference between the charge glass state and charge crystal states. In the charge glass states, so the optical conductive spectra shows a very broad peak, while in the charge crystal states, there are several characteristic features, such as a clear optical gap, this very sharp nu3 peak, and also deep structure coming from the overtone of nu3 mode. But so we measure the optical conductivity spectra in the slow cooling process, and so as you can see, this characteristic feature are smeared with increasing irradiation time and above 80 hours. So actually, these features disappear, which means that above 80-hour irradiation, the charge glass state is realized, even in the very slow cooling rate. And also, of course, in the rapid cooling process, you always observe this charge glass state for all the irradiation time. So from these results, we can say that the optical conductivity spectra in the charge glass state realized by rapid cooling and X-ray irradiation are very similar. So there we cannot observe any difference between these two charge glass states. And then, so we also perform the DSC measurement for the X-ray irradiated sample, and we made TTD diagram as shown here. And as you can see, the charge crystallization regime shifts to a longer time region with increasing irradiation, and also the peak temperature decreases with increasing irradiation time. So the result indicate that charge crystallization is significantly suppressed by X-ray irradiation, which lead to a lower critical cooling rate compared to that of the crystalline sample. Okay. So finally, I want to discuss the origin of this irradiation effect. So as I've already discussed, the glass formation mechanism is dominated by the geometrical frustration of the triangle lattice. But actually, in addition to this geometrical frustration, randomness is also a very important factor for the charge glass formation phenomenon, charge glass formation in this type compound. So this is my message. Okay, so this is a summary of my talk. So in this presentation, I show the I compare the compared optical conductivity and resistivity in these three different materials, and we found different charge glass formation mechanism in the orthonomic and monoclinic system. And we also found that the randomness effect is also a very important factor for the charge glass formation. Thank you very much for your kind attention.